Good afternoon, everybody. Hope you had a good lunch, and thanks for coming back for our talk. This is Kankani, a platform architect representing Uber's infrastructure team, and with me, my colleague, Ling, who's a software engineer in the ML platform team. We are both here to delve into the challenges and opportunities as we navigate through the path of effectively scaling Uber's infrastructure for AI ML use cases. Our talk will be focused on meeting the demands of highly upcoming and dynamic generative AI use cases. We'd like to invite you all to join hands and explore the hardware-software co-design solutions and engage in the OCP community, especially the CXL enablement for AI/ML workloads. And we believe together we can drive this innovation and share our learnings on how to efficiently scale infrastructure. So with that, I would like to delve into how ML is deeply integrated into every facet of our business. Taking a look at the Rider app, ML is used behind user authentication, ranking and recommendation of products, ETA predictions, pricing strategies, driver-rider matching, and even in our efforts to prevent payment fraud. These are just a few examples of how ML pervades and enhances the overall Uber experience. Now let's delve into the Uber ML lifecycle, starting from model development to productization. At Uber, the data is stored in our data lakes managed by our data infrastructure team. To kickstart the process, we have a bunch of Spark jobs to load, prepare, and transform features within this data set. And these transformed features are then stored in the basis feature store. In parallel, we have a lot of streaming data from Kafka that we harness, which is used across various models and stored in either real-time or batch feature store. Moving on, we perform multi-node training jobs using our training module. And these models are then stored in internal model store for internal checkpointing, operational management, etc. And finally, these models are served through real-time or batch prediction services. Now, throughout this journey, we face a multitude of infrastructure challenges that impact our operations. To start with, we face and deal with a lot of I/O bottlenecks during reading the data from data lake. The transformation process on the Spark jobs, we face a substantial compute and memory capacity challenge. Moving on to the training phase, we not only face another round of I/O challenge, but also require high teraflops and network bandwidth constraints. And finally, in serving, we require memory bandwidth for meeting acceptable serving latencies. So all in all, these challenges, in one way or the other, slow down our training process and also limit the volume of data that we can train with. To further understand the scaling challenges, let's take a look at the evolution of ML models divided into 3 distinct phases at Uber. The first phase started back in 2016 when our ETA and pricing strategy teams started to look at the feasibility of moving some complex rule-based systems to machine learning models. At that time, our CPU-centric infrastructure was capable enough to host these models. Back in 2019, the second phase, we embarked in the second phase where most of our business-critical use cases were using ML in their core flow. Until then, our models were mostly tree-based, like XGBoost, and deep learning just started to take off. And fast forward to now, 60% of our tier 1 use cases are using deep learning models. And these models require GPUs, and we are also looking at the CPU and GPU heterogeneous architectures to enhance the infrastructure efficiency. The third phase started recently with the advent of GenAI, and we are exploring the end use cases for GenAI at Uber. And this invariably requires substantial GPU capacity in hundreds and thousands of GPUs, and in order to meet the reasonable training times and acceptable serving latencies. Now let's delve into the GenAI workloads a bit further. At Uber, the GenAI efforts are centered around three primary implementation options. On one end of the spectrum is prompt engineering, where we use enterprise vendors' large language models straight out of the box through their APIs. This gives us the fastest time to market, but also comes at a higher cost. On the opposite end of the spectrum is using the pre-trained foundational models with massive data sets. This is the slowest approach, as it can result in training times spanning days, weeks, even months, and requires substantial GPU investments, and hence comes at a very high total cost of ownership. In between these two approaches lies the fine-tuning approach, where we use models like Meta's Llama 2 model and tailor it for Uber's specific needs and use our own data sets. This is quicker in terms of training times and comes at a lower cost of ownership because we host it in our on-prem or cloud infrastructure. Now, the fine-tuning can further be divided into two distinct strategies. Full fine-tuning, where we adapt all the model hyperparameters for a specific task, and parameter-efficient fine-tuning, where we only adapt a subset of parameters. From the infrastructure standpoint, our strategy is to use the existing ML infrastructure and get the maximum out of our current resources for the parameter-efficient fine-tuning. For the full fine-tuning and pre-trained models, it necessitates both scale-up and scale-out upgrades. This means technologies like NVLink, full mesh NVLink across all GPUs, upgrading the network link bandwidths, managing congestion controls, establishing dedicated racks, and optimizing network topologies, to name a few. Now let's move forward by defining some specific key results and metrics that we need in order to meet our goal of optimizing existing infrastructure and building new infrastructure for GenAI use cases. The first one is feasibility and reliability. Users engaged in ML training expect their models to converge without errors within a reasonable amount of time, days, sometimes weeks. Moreover, they also expect high training stability, north of 90-95%, to maintain consistent and reliable results. The second is efficiency. We constantly prioritize and benchmark various GPU system configurations, accelerators, CPUs, in order to get better price-performance ratios for specific workloads. We measure efficiency in terms of teraflops, model flops utilization, and training times. Our goal is to make sure the GPUs are not idle, and we enhance and maximize the utilization of GPU resources. And lastly, the developer velocity. We measure developer velocity by the number of experiments our engineers can run in a period of time, and time to productionize a model. We also enhance developer velocity by prioritizing maturity of the ecosystem, like CUDA compilers and PyTorch frameworks and so on. So in meeting these goals, we do encounter a few challenges. It is hard to design an efficient AI/ML system design for the diverse workload requirements of AI landscape. Like we saw from XGBoost to deep learning to large language models. For example, large language models requires high compute density and teraflops, whereas deep learning can be memory bound. When sharing GPU capacity across these different applications, we sometimes conservatively allocate resources in order to ensure fairness and equal distribution across applications. So this can result in lower utilization levels. Another challenge is open source libraries and optimizers and integration of that within Uber's production containers. We have Uber ML framework, Michelangelo, and we are looking at developing the end-to-end LLM support within that framework to enhance developer velocity, and that's work in progress. Memory expansion, both in capacity and bandwidth, has not kept pace with the scale at which the model hyperparameters have grown, and that's a big challenge. Probably you have heard that many times in this conference so far. And last, but probably the most important one, is scaling of the network resources, bandwidth, in both scale out and scale up setups. To enhance the training efficiency, this is needed. Now we'll delve into a couple of case studies that talk about these challenges. The chart on the left depicts the Uber ML's GPU fleet, reservations, and allocations within the past month. What's evident from this chart is that our allocation rates are very modest and much lower than where we would like it to be. And this phenomena is, the reason for this is the newer workloads are requiring more and more system memory per GPU worker than what is currently available on the systems. The inherent limitations of number of DIMM channels on the server prevents us from scaling up these allocations and unlocking further efficiency. This is precisely where CXL memory expansion can help in unlocking further GPU allocations, increasing the memory, and further improving our efficiency. Here we show the results of the summary of our results for a large language model use case, and the significant impact of network improvement, both in terms of bandwidth and congestion control management, in getting better training efficiency. What we see here is a twofold improvement in throughput for training and a significantly reduced training times when we use NVIDIA's DGX setup, which is equipped with InfiniBand congestion control management techniques and even higher link bandwidth compared to our on-prem machines with Ethernet and a lower link bandwidth. When we do multi-node training, there's a lot of duplication of data that happens across nodes that puts pressure on local memory and even on the network I/O. And we believe this is the place where CXL memory, pooled memory systems can help us in scaling memory across various systems. Now we look at our design framework and experimentation approach for offloading optimizer states for a large language model from like Meta's Llama 2 model from GPU memory to CPU and NVMe devices. Our objective is to assess the impact of this offloading of parameters and optimizer states from GPU to NVMe devices and CPU memory to look at the GPU scalability, training efficiency, and some other system metrics. For this setup, we have used our on-prem ML machines equipped with NVIDIA's A4 A100s and Intel Ice Lake CPU. We have a cluster of 32 GPUs across 8 nodes, uses Ethernet fabric. So from here on, my colleague Bo will go over in detail about the LLM training architecture and describe our experimentation results. So over to you, Bo. Take it away.
Yeah. Hi, everyone. So now I will talk about our large language model training and also our efforts to optimize the training efficiencies. So first of all, let me first sketch our large language model training architectures. So at the top level, we use a ray trainer to do the distributed training because Ray provides a sync API to perform distributed training, and Ray can configure all the distributed process group for us. At the middle level, we are using Hugging Face transformers and also Microsoft DeepSpeed. And the Hugging Face transformers has a very nice API to download model and perform the training loop, update the gradients. And DeepSpeed is a very nice library to do model parallelism. It contains zero infinity with several stages. At the bottom level, we're using Torch to do the distributed training because the Torch basically supports most of the state-of-the-art natural language model and large language models. Also, we use Nico to perform the multi-node, multi-GPU network communications. Okay, Now, let me talk about our training pipeline design. Our training pipeline design actually very simple. Basically, it's reading data from storage, distributed training, and then model checkpoint management. So for distributed training, as we said, we use Ray to manage start multiple workers. And in each worker, we use Hugging Face transformer, including Hugging Face accelerator and the Microsoft DeepSpeed to do the gradient updates and also manage the partition states. Partition states basically is the states after you do model parallelism. So let's talk about why we need a model parallelism for large language model training. So distributed training basically, based on my understanding, there are kind of 4 scenarios you can use, which is a data parallelism and also 3 stages in DeepSpeed 0 infinities. It depends on whether how much you want to copy your model states across the different GPUs. So without model parallelism, you can do a simple computations. Each billion of parameters requires 16 gigabytes to train. So if you want to train a 3B, which is a T5, which is a sequence-to-sequence smallest large language model, you can think it's a T5 3B. You need a 48 GB memory to train. So if you want to train a large model with even more GPU, it's let's say, so with 180 GPU memory, the largest model you can train is just 5 billion model parameters. Instead, if you want to use, if you enable the model parallelisms, the 0 infinity stages can sharded your model states, including model parameter gradients and optimizer states across the different GPUs. So you can scale to any arbitrary number of billion parameters models as long as you have enough GPUs. So given that, I want to talk about our experimentation training on Llama 2 70 billion models and our optimization and our share our findings. So, so as I said, for large language training, you definitely need a model parallelism. Actually, find offloading provided by Microsoft DeepSpeed as actually also very important. Here, the left panel, I have several graphs, but all the left panel is training using GPU memory only, and the right panel is with CPU or NVMe offload. The first graph is about the CPU memory usage. Here we can see if you just train on purely GPU, your CPU memory is actually very low, which actually is not a good thing because you are wasting of the GPU resources. But if you use CPU offload, actually your CPU memory can be fully well utilized. If you check GPU memory, if you train just using GPU, then you almost meet the capacity of your GPU memory. And what we find is that most of the large language model training actually bounded by the GPU memory because you cannot increase your batch size a lot. Otherwise, you will get a GPU memory error. But with the CPU offload, basically you can reduce your GPU memory usage. Actually, here we even increase the batch size. The batch size we increase it from 2 to 6. We still see the GPU memory usage with offload still 34% less than the using GPU training purely. Another thing I want to show is our GPU utilization. And with the CPU offload, we do observe some GPU utilization has some dips. And we suspect is because we need less compute communication. That's why, and also our batch size is larger. That's why we have some kind of dips. But that we need further kind of investigation how to optimize the deep speed. Most importantly, actually, one thing we find is if you use a CPU offload, your network throughput requirements actually less. That actually can reduce the inter-node communication overhead during large language model training. So here I want to go to our result summary. So first of all, we are able to train large models that cannot fit with a limited scale GPUs, especially when turn on the offload. And also offload can result in better training efficiency because we can enlarge the large batch size. Otherwise, your batch size is limited by the GPU memory boundary. So we actually find the GPU memory, as we said, the GPU memory is used 34% less, but the MFU, which is the metric to measure training efficiency, actually more than two times larger. And we also find that network throughput actually is smaller if we turn on the CPU offload. And so the high bandwidth and the low latency CX device could maybe further improve the training times. Okay, here's some next steps ongoing and on our ongoing effort. So first of all, we need to improve the training stability when using deep speed offload. So the deep speed library is very rich. It has a lot of offload operations. Now we still try to figure out the best one to improve the training efficiency. Also, we need to continue to try the larger models. Right now, we are trying Llama 2 70 billion. But now, these days, there's another open source large model, is Falcon 180 billion. So we need to try that one. And also, we need to try larger cluster size to see whether our assumption with offloader can hold or not. So after model training, we need to run batch inference. So right now, we try to optimize the batch inference with offload as well. Because if you increase your model a lot, and it cannot fit a single node, let's say 320 gigabytes with a 4 GPU in one node, then you definitely need a model parallelism to the model inference. The other part that we already get a kind of exciting result when we try to do reinforcement learning. So next thing, we need to evaluate the GPU training on CXL attached memory to see whether we can further get some improvement of our training efficiency. With all that, I will give back to my colleague, Navneeth, for the conclusions.
Thank you, Bo. So to wrap up, we'd like to leave you with 3 key insights. It is hard to do an efficient AI/ML system design in the face of rapid evolution of models and applications. And hence, scaling of infrastructure efficiently requires hardware-software co-design across different layers of the stack, and innovation is needed. Through these experiments, and we have demonstrated the impact of scaling up memory, network resources, and even memory offloading on enhancing the training efficiency for generative AI models like Meta's Llama 2 model. And lastly, we'd like to extend a call to action and urge all of us to actively participate in CXL enablement for AI/ML workloads, foster industry partnerships, and leverage open source optimizations. Together, we can drive innovation and tackle the evolving demands of GenAI use cases. With that, thank you for your time, and enjoy the rest of the conference.